Hello, this is section 8.2, Inference for the difference of two proportions. So we're going to be doing testing two proportions, P1 and P2. I often call this the two-prop z-test. Now the requirements are that we have a simple, random sample for both samples, which I abbreviate SRS. The samples must be independent. And then the number of successes in sample 1 has to be greater than or equal to 10. The number of failures in sample 1 has to be greater than or equal to 10. The number of successes in sample 2 has to be greater than or equal to 10. And then the number of failures in sample 2 has to be greater than or equal to 10. Oftentimes, I'll call this third requirement the size requirement. And then here's the test statistic. So the p hat 1s, p hat 2s are the sample proportions. P1, P2 are the population proportions, which we're making a guess at how they're related, but this comes from the null hypothesis, or H naught. Then you have P bar, which has the formula over here of x1 plus x2 over n1 plus n2. And then n1 is the sample size of sample 1, and n2 is the sample size of sample 2. A common formula you'll need to know as well is that p hat is equal to x over n, or x is equal to n times p hat. And those are true if you're talking about p hat 1, n1, or p hat 2, n2. Now, because that is a z-score, the distribution used is a normal distribution. And what that tells us is if we do the critical value method, we'll be using Q norm. And if we do the p-value method, we'll be using p norm. And then the R function is given below. I'm not going to read through it, but we will use it in the examples. The one part I do want to point out, though, is that we are always going to have correct equals false. We aren't going to use the normal continuity correction. Okay, example 1. A study of 200 randomly selected occupants in passenger cars and 250 randomly selected occupants in pickup trucks shows that 91% of occupants in passenger cars and 83.2% of occupants in pickup trucks wear seatbelts. At alpha equals 0.10, can you reject the claim that the proportion of occupants who wear seatbelts is the same for passenger cars and pickup trucks? So the first thing I need to do is check my requirements. So it does say randomly selected, so SRS checks off. I am going to assume that people that drive cars is independent from people that drive pickup trucks. So independent. True. And now I have to check the size requirement. Now, I do not know the number of successes or failures for either pickup trucks or cars, but I know the percentage of successes. So to calculate the number of successes, I'm going to be using the formula x equals n p hat. So for passenger cars, I get 200 times 0.91, which is 182. That is the number of successes. Then the number of failures would be 200 times 1 minus p hat from what we said on the previous page, so 0.09, which is 18. Then if I do the same thing for pickup trucks, that would be 250 times 83.2, That comes out to 208. And then if I take 250 times 1 minus that, which is 0.168, that'll come out to 42. So the size requirement is saying that all four of these values need to be at least 10, so we meet our size requirements. So we can perform a two proportion z-test. So just like with any hypothesis test, you start out with the claim and hypotheses, draw a picture, calculate a test statistic, then calculate a p-value or critical value, one or the other, and then make a decision and conclusion. So let's start with the claim. So the claim here is that it's the same, so that p cars is equal for p trucks. Just like in the two sample mean case, though, for the two sample proportion case, we are going to want to subtract that. First of all, that if we were doing the formula by hand, that would tell us which way to subtract it in the formula. And then if we're using the R function, that tells us in which order we have to type the data in. So because I'm doing PC minus PT in this example, I would have to do type in cars first, trucks second. Now, it doesn't matter which way you subtract it, just as long as you stay consistent in your own problem. The opposite of this, then, is PC minus PT is not equal to 0. The null hypothesis is PC minus PT is equal to 0. And then the alternative hypothesis, which comes from the claim or the opposite, it's not always one or the other, it can be either or. It's just you have to pick the one that does not have an equal to part. In this case, it's the opposite, so it's PC minus PT cannot equal 0. Step 2 is draw a picture. Since my alternative hypothesis is not equal to 0, it is a two-tailed test, and it's from a normal distribution, so I got a bell curve. Alpha, which is the area of all the shaded regions, is 0.10, so that means each tail has to be 0.05. Now I'm ready to calculate the test statistic. The test statistic is going to come from prop.test, which I'm going to now switch over to R to do. So prop test, and then x equals the two x values. So that would be the 182 and the 208 that we calculated. Again, going cars first, trucks second. N equals, we had 200 cars, 250 pickup trucks. Then we go alternative equals 2-sided. Confidence level equals, well, we were given alpha, which was 0.10, so confidence level will be 0.90. And then don't forget the correct equals false. I forgot to put the C in front of the parenthesis for N. And there we go. There is the prop test for this. Now, as a reminder, it does give you the p-value right here. This is p hat 1. This is p hat 2. This is technically the confidence interval, but we aren't going to do that in this class. And this is normally where the test statistic is. But notice that it says squared. So we need to take the square root of it, though, to get the actual test statistic. So there's our test statistic. I'm actually going to take a screenshot of this to copy over into the notes. There we go. Okay, and now I'm going to switch back over to the notes. So there, I copied and pasted it. And I'm just going to copy down the pertinent information. So our test statistic, which is Z, is equal to 2.42. And then our p-value is equal to 0.0156. So there we go with that. And now it's time to make our decision and then our conclusion. So since the p-value is less than alpha, because alpha is 10% and 1.5% is less than 10%, this implies that we reject the null and support the alternative. And now for the conclusion. If I scroll back up to where my claim was, the claim matched the null hypothesis in this question. So what was my decision about the null hypothesis? I rejected it, so I'm going to reject the claim. So there is enough evidence to reject the claim that the proportion of people that wear seatbelts is the same for car drivers and truck drivers at the 0.10 significance level. Essentially, we're saying that there is a difference. Now, because this was a two-tailed test, I can't say which one has a higher proportion or which one has a lower proportion. All I can say is that there's a difference. Example 2. A medical research team conducted a study to test the effect of a cholesterol-reducing medication. At the end of the study, the researchers found that of the 4,700 randomly selected subjects who took the medication, 301 died of heart disease. Of the 4,300 randomly selected subjects who took a placebo, 357 died of a heart disease. At alpha equals 0.01, can you support the claim that the death rate due to heart disease is lower for those who took the medication than for those who took the placebo? The first thing that I notice in this problem is that I'm not given any percentages or fractions. So that means I wasn't given p hat, so I must have been given x, or the number of successes and number of failures, which we were. 301, 357, and then the complement of those would be subtracting them from the 4,700 and 4,300 respectively. So let's conduct our requirement check. So SRS, yep, randomly selected. Independent, yes, because you either took the medication or you took the placebo. And then we had 301, 357 successes. And I'm not going to do the subtraction because 4,700 minus 300 is definitely bigger than 10, and 4,300 minus 357 is definitely bigger than 10. So just by close inspection, my size requirements does meet. So now I can go through and do the 2 prop Z test. So again, I need to start out with my claim. So the claim is the death rate due to heart disease is lower for those who took the medication. So PM is lower than P placebo. And again, I need to subtract. So my claim comes out to be the difference of the proportions is less than 0. The opposite of that is that the difference of the proportions is greater than or equal to 0. The null hypothesis is always equal to. And then the alternative hypothesis, again, has to match this or that, whichever one doesn't have the or equal to part. So this time, the alternative hypothesis matches the claim. And because of that, because it's less than 0, we are going to have a left-tailed test. And it's a normal distribution, so I'm going to get the bell curve. And our significance level was 0.01. So now I'm ready to do the test statistic. So I'm going to go over to R. Let me just erase this. Okay, so prop dot test X equals, and I need the medication first, so 301. Don't forget the C. So 301, and then 357, and then N equals, again, medication first, so 4,700, 4,300. Alternative equals less. Confidence level equals 0.99, because that's 1 minus 0.01. And correct equals false. Let me just remove some of these spaces so it all fits on one line. There we go. There is my prop dot test. But again, this isn't the test statistic. That's the test statistic squared. So I have to take the square root of 11.938, and that gives me my test statistic. Before I switch back over to the notes, I do want to do the critical value method time, because you'll need to do it on the homework. And notice none of these numbers in the prop dot test is the critical value. So remember, we're doing a left-tailed test, so the critical value is going to come from Q norm, 0.01, 0, 1, and because it's a left-tailed test, lower dot tail equals true. So there's our critical value. And this actually does bring up a good point that I almost forgot to mention. But don't forget, this square root could be negative, and you won't be able to tell. But if I look at p hat 1 and p hat 2, if I do 0.064 minus 0.083, that's going to come out negative. So when I do my test statistic is actually going to be negative 3.455. Okay, and now back over to the notes. So my test statistic, which is Z, is equal to, again, the negative 3.46, I guess, if I round to two decimal places. And then my critical value, which I guess I'll call ZL for this one, is negative 2.33. Now you could use the p-value because it's given to you, but I want to remind you how to do the critical value test. Is we go back up to our picture, the negative 2.33 represents that cutoff line. And negative 3.46 is over here in the shaded region. So that tells us our decision is to reject the null and support the alternative. Okay, so now what's our conclusion going to be? Because my conclusion shouldn't talk about the null hypothesis or the alternative hypothesis. My conclusion should only talk about the claim. So when I go back up here, my claim matched my alternative. So what did I do to the alternative? I supported the alternative, so I'm going to support the claim. So there is enough evidence to support the claim that this medication lowers your risk for heart disease at the 0.01 significance level. And then finally, example 3. There's an old wives' tale that women who eat chocolate during pregnancy are more likely to have happy babies. A pregnancy magazine wants to test this claim, and they gather 100 pregnant women for their study. Half of the group agrees to eat chocolate at least once a day, while the other group agrees to forego chocolate for the duration of their pregnancy. A year later, the ladies complete a survey regarding the overall happiness and contentness of their babies. The results are given in the table below. At a 0.01, test the old wives' tale. So here, you have to determine, are we comparing happy babies to unhappy babies? Are we comparing the mothers who ate chocolate to the mothers who didn't eat chocolate? And it can be confusing sometimes. In this specific case, we are comparing with chocolate to without chocolate. So that means my N1 would be 50 because that's 24 plus 26. And my N2 would also be 50 because that's 22 plus 28. And then we need to determine which counts as the success, the happy babies or the unhappy babies. Well, the happy babies. So X1 is the 24 and X2 is the 22. And then the 26 and 28, we needed them to calculate the totals, but they won't be used in the calculations from this point. So now, do we have a simple random sample? Yes. Are they independent? Yep, because you have different women eating chocolate and different women not eating chocolate. And then thankfully, this table actually lists out all the successes and failures for us. So are they all at least 10? Yes. So we meet the requirements for this one as well. So we get to do a 2 prop Z test. Start out with the claim, which I think that is saying the proportion of happy babies with people that ate chocolate is greater than the proportion of happy babies that did not eat chocolate, so without. Do the subtraction. So there's our claim, is greater than 0. The opposite would be less than or equal to 0. The null would be equal to 0. And then the alternative matches the claim again. So PC minus PW is greater than 0. Since our alternative is greater than 0, that tells us that we are doing a right-tailed test, this time for the bell-shaped normal distribution. And we have 0.01. That's quite a low significance level for a study of this magnitude. Okay, so now I'm going to go over to R to get my test statistic. Clear that out. Prop dot test x equals collection. And now I did PC minus PW, so the chocolate has to come first. So 24 comma 22, n equals collection, 50/50. Alternative equals greater. Confidence level equals 0.99 again. And then don't forget the correct equals false. We get that test, our test statistic, again, would be the square root of the 0.16103, or the 0.4. And again, I don't want to forget, like I did in example 1, I'm going to look at prop 1 minus prop 2. Well, 0.48 minus 0.44 is positive, so that should be a positive critical value. Let me take a screenshot so I can put it in the notes. And then go back over to the notes. So our test statistic is the positive 0.40, and our p-value is the 0.3441. Now, since our p-value is greater than alpha this time, because alpha is 0.01, that implies we fail to reject the null, and we fail to support the alternative. So there's my decision. But again, the conclusion should always be about the claim, not the hypotheses. So if I go back up to the top, the claim matched the alternative again. So we fail to support the claim. So there's not enough evidence to support the claim that the proportion of happy babies is more with women who eat chocolate during pregnancy versus those that don't at the significance level of 0.01. And that's the end of section 8.2 notes.